Hello everyone, I'm Tiago. I'm a PhD student here in Lisbon at the Systems Neuroscience Laboratory at the beautiful Champagnat Research Center. I'll be giving a talk that I am concerned may be a bit outside of the rest of the talks given in the conference, so please feel free to question me in whatever ways you would like in the end. I would just like to start by acknowledging the beautiful artist that made this illustration especially for my project, where a human attempts to figure out the best way to achieve that temple on the top. And that process is a bit what I'm going to talk about. How do we make decisions, and how do we choose the best route to the best decision? Now, learning a complex skill has been a very widely researched topic, including in the field of linguistics, for example, in natural language processing, or in the famous chatbot ELIZA, for example. And scientists started off by using approaches that would grab some heuristics or some knowledge that we have about the structure of how these skills are developed. For example, in language, we could start with some grammatical structure or something like that. But lately, in the 2010s or even in the early 2000s, a big explosion occurred with the development of associative approaches, approaches like deep neural networks or other types of explorative approaches that allow these algorithms not to have any priors when going into tackling a problem such as these. And this was something that some people were very cautious of, or didn't accept so quickly. But one thing we know, and that was a shock to a lot of people, was, for example, one of the best translators that we know, automatic translators that we know, Google, shifted into a completely neural network driven mechanism as early as in 2016. And according to not only blind tests, but also in the quality as analyzed by a lot of researchers, for example, here, they indeed improved a lot, even though they ditched what was once thought as the golden standard for these types of approaches. Now, if we ask an algorithm of any sort to one of the things we can ask them to explore is, for example, to solve Atari games. These are very simple video games, and they are chosen because they are simple, and where humans have had decades to figure out the optimal strategies. And what we can see here, for example, in this plot, is that the performances of humans are extremely high, but with only a few hours, the more complex the algorithm becomes, that's from dashed to the dot, that is, the more information you allow, and the more you allow the algorithm to build its own model of the Atari system, the better it performs and the closer it performs to the human, even though it takes a lot more hours. Now, how do we build these skills? How do we figure out how to play an Atari game so fast, for example? There are two different possibilities of approaches. One that I'm calling the bottom-up, and the other one I'm calling the top-down. In the bottom-up approach, we look at what these more exploratory algorithms do. For example, they are given a landscape of values, and they are said to navigate this landscape as they see fit until they find the best possible outcome. Now, in the top-down approach, it's a bit different, because in that case, you start with some sort of local maxima that you have an idea about, say, for example, your knowledge of Portuguese grammar, and then when you try to learn the English language, you are going to adapt some of those skills into the other skill. But the difficulty there, as we all know, for example, again, using the example of language, is that sometimes when you know a certain rule set, you get a bit stuck on that, and it's hard to jump between, for example, one local maxima to another one that may be best. So there are a few questions that I'm going to pose are what determines the space of possible policies to navigate these state spaces? How are these policies learned? When do they change? And the challenges that we faced are that behavior is extremely complex, it's hard to code, it's hard to understand, to induce, to sample, to generalize, and all of these were concerns that we had when we started thinking about how we could tackle this problem. So a lot of people have tried to do this in a few environments. For example, one of the very interesting attempts is done in a game that is similar to Simon Says. I don't know if everyone knows this game, but it's lights go on in order and you have to follow lights in order. And there are some transitions that are stronger than others. For example, from here to here, it's more common than from here to here. And then what you can see is that people follow either some hierarchical strategies or some pruning strategies where they just drop, for example, a certain sequence is too hard, they just drop that one and follow another one instead. Or they follow the first 3 lights always, but then are unable to reach the next ones. Another thing that people have widely studied is the games like chess. But chess, as we know, is slightly problematic because of its, the nature of its complexity. It's an extremely hard problem. But even then, what we know is that it's possible for us to quantify the level of expertise that it takes to change, for example, from being a novice into an expert, or even analyzing different types of plays, you can realize the level of expertise of a person. But all of these experiments done in these environments seem to be a bit too broad to study the hypothesis that I put up in the beginning. So an approach that we were very interested in following is that of adapting the field and the techniques of psychophysics into these high-dimensional spaces. So why is that? So psychophysics are techniques that allow us to model in much more detail, for example, using drift diffusion models or reaction time curves, etc., more accurately the behavioral phenotypes of certain subjects. The actions in these psychophysics tasks inform the intent of the users. There are specified states, actions, and rewards that we can quantify and model. They are easy to generalize to several problems. We can have procedural stimuli, and most recently and interestingly, they can be gamified. They can be made into platforms that allow us to collect extremely large amounts of data. So, for example, what we started for was something similar to a traveling salesman problem. I don't know if you're familiar with it, but it's very simple. The idea is, say you are asked to visit all the capitals of Europe in the minimal amount of steps and distance possible between them. And you would probably come up with something like this, similar to this. And this problem is a problem that is quite intuitive for us humans to solve, but it has taken decades for algorithms to become good at. Another example is, say you are now at a hotel staying here at Intendente, this beautiful area of Lisbon, and you want to come here to Praça de Espanha where the conference is held. If you've never navigated the metro of Lisbon, it's quite intuitive that probably what you should do is either go up and then here, or maybe go down and here to minimize the number of line traversals. But the basic idea is that we have some heuristics that come with our lives, as I said in the beginning. For example, I I don't like to swap lines. Swapping lines is expensive, so I would optimize going down and then up. Or I prefer minimal distance. In that case, I would go up here. And all of these extend to any type of metro or any type of problem of this sort that we have. So we implemented a problem like this, but in the framework of a video game. Basically, this video game, you are faced with these triangles that are growing in value from 0 to, from 0, for example, here there's a 2 triangle, here's a 5 triangle, here's a 6 triangle. So they basically grow. And the idea is you have to collect the triangle as large as possible by just clicking the triangle. And with one target, it's trivial because it grows and you're supposed to collect it at the maximum and then you get the maximum value. Now, with 2 triangles, that's when the first dilemma starts, and that's most interesting. If you have 2 triangles and they are one next to the other, it's very trivial because all you have to do is collect one when it's largest, then move, then collect the other one when it's largest. Oh, I forgot to say something very important, which is every time you move, the entire board moves outwards. So, for example, in this case, if you were to move here, what would happen is that this one would grow too large and you would lose it. So what you have to do is a non-trivial problem, which is choose to sacrifice points in the first triangle, illustrated here, so that you can get to the second triangle when it's maximal. Because if you grab the first triangle when it's largest, given that everything expands, this one will expand too large and you will lose the points over there. Now this problem explodes in complexity when you start presenting with more pieces of the puzzle. And now, instead of having just this type of dilemma, you start getting inserted with other types of dilemmas. For example, the one that I posed to you about the metro. What order should I collect these pieces in? Or what is should I skip one and then come back to it, for example? And these are here in the bottom panel. Maybe they're a bit too hard for me to explain, but basically they're landscapes, value landscapes, and they're hypercubes that basically contain all the state spaces of strategies, like in the first plot that I showed with the top down. And these here, the tips, are the local maxima that a player needs to jump from one to the other in order to achieve optimality, the harder the puzzle gets. Now, here's an example of gameplay where basically a volunteer, it's me, performs this game, highly trained, because I spent hundreds of hours doing this, but the idea is that you should see and observe that some behaviors are very interesting. For example, some people, they count. Like in the metro, you could count how many stations away are you before you commit to a decision. Others commit to other types of heuristics, like they always like to go around and never go back and forth. And as we increase the number of targets, of course, we induce complexity in the policy spaces. If they are ordered, it's trivial. You just have to go always in a straight line. But if they are not ordered, like in this case where you have to go back and forth, then you start introducing a lot more difficulty. Now here, for example, I'm showing you just in type of puzzle from blue, which is ordered puzzles, to slightly less ordered, completely chaotic. I'm showing you the connections between how many moves are different from one puzzle to the other, and you can see that very quickly you can create a space that is too dense for us to, at least consciously, have in our brain. So we must be using other types of strategies instead of a totally associative and explorative approach. Okay, so here's some data. What I can show you first is that the total, in this axis I'm showing the total amount of rewards that people acquired and the number of targets. So this means progression in the game. And basically in blue you have humans, and in color you have the models that we trained on this task. And what you can see is that humans are extremely fast in the one target level, and models are very slow, are much slower. Now, the more we increase the difficulty, the more the models catch up, but still they require a lot more to be able to clear the levels, whereas humans don't need that much points to clear the levels because they're using better strategies. And you can see here also in the attempts to pass, given the level number, that means the complexity in the puzzle, that optimally you should take always only one attempt, of course. Humans are almost optimally until they reach harder levels, and inversely, all the agents are much worse until they reach very, very highly complex puzzles. Now, one thing we do know is, for example, that in humans, the priors that humans have, which is, this is the first time they ever try it on a two-piece puzzle. For example, we know that humans are very greedy and they like to collect things in order. So in red, you have people starting at a very, very highly optimal scenario where agents don't start so optimally. And then once you get into the end of the level, humans converge in both strategies, even the hard strategy, the non-greedy or the greedy, to very high performances. Where instead, the agents, they not only fail to converge in both, but they also fail to reach the same level of performance that humans get in this type of puzzle. Now, as we increase the complexity, as I already hinted, something very interesting comes up, which is humans stagnate on the fraction order. That means that they insist on collecting targets in order instead of adapting these more elegant strategies that you need to solve this puzzle optimally. Instead, these agents quickly learn that they have to drop this strategy of collecting in order and they start collecting more erratically to maximize their scores. But networks still optimize into suboptimal policies, meaning that the humans are losing a lot less points. They're willing to sacrifice less points. Even though they're not reaching such high scores, they're losing less points. And if you look at the fraction of targets collected when they are at their fullest, in black, again, we have the optimal line. This is the difficulty. We see, again, that humans are almost flat, whereas agents learn that they should collect more fully. Now, to end, I would just like to show here examples of two subjects and two networks, and something that we are extremely interested in, which is what we believe is the greatest insight we can get from this study. If you look at these examples, you see subjects navigating a certain type of space. For example, here they're always using this is again, sorry, the same axis, the fraction of collected in order. They're using a certain strategy highlighted so the colors are the levels. I'm sorry, I forgot, for some reason it disappeared, the legend. The colors are the levels, and what we find that is extremely interesting is that at some point, after losing a bunch of times in this level, this specific subject chose to jump from collecting it in order to start exploring completely erratically. Now, this happened consistently to all of our subjects. Here's example subject number 2. At some point, after losing a bunch of times, he changed order and then was able to progress. But instead, the networks, they never seem to fall in this type of bottleneck of strategy. Meaning that, meaning that humans are somehow getting stuck in these local maxima that for one side, they help them optimize and start off with an edge. For example, when we travel to a foreign city, we know how to navigate the metro map, but it's not intuitive that that's the optimal thing that we should be doing to solve these types of problems. And that could hint, for example, why these artificial neural networks are consistently overperforming humans in various types of tasks. So I introduced a task to parametrically sample complex skills. We showed that humans learn similar strategies regarding of the difficulty, that strategies are flexible but very hard to discard once they are acquired. We show that strategies only change after persistent failures. We show that unlearning previous strategy gives ways to mastery, and also that humans differ. We don't really show that, but we are hinting that humans differ to these types of more compositional strategies instead of the more associative strategies. Now, in the future, we're launching this game online. Just a little teaser. This is what it looks like right now. It's we had the help from professional developers, and we're going to use this to collect large samples of data so we can have statistical power, basically, to make the claim that I'm trying to make. In the end, I would just like to acknowledge my lab, my supervisor, Zachary Mainen, my collaborators, Gautam and Mattia, all of my lab, and the conference for the invitation, and of course these guys, the game developers, our funding from BL, and the Champalimau Foundation. Thank you.